So hi everyone, my name is Kirill. I've been in the AI space since 2017, starting as a ML AI researcher, then managing teams and products. Then in 2021, I entered Web3 space, initially building indexing platform based on the graph. And now I work at Nethermind and working on various projects on the intersection of AI and Web3. Including a few ones that I will mention, I guess, in the end. But the most notable, and which is already on production, is Audit Agent, which is the AI smart contract auditor. On this example, we were kind of diving into AI agents actually in Web3 and making some kind of utility agent. Today, I want to explore the topic of building effective agents using LLMs, I want to present it in a way of the kind of new other way of building software, more kind of smarter software, which came with the LLMs, and the LLMs appeared with some new patterns that we have to master to actually build something usable, reliable, and making some new values, creating some new values for us as developers or as users. So some insights. So one consistent observation is that most successful implementations of real-world agents aren't the most complex ones. So simple, composable building blocks are actually causing like going to the much more sophisticated, much more reliable agents and much more usable agents compared to those which are which we can get using some sophisticated framework. So this is one of the observations, that starting from scratch is not usually the worst scenario. When we keep it simple, so we can measure something that we cannot measure when we use frameworks. And actually, when we start building with frameworks, it's easy in the beginning, but when you start debugging it, you get a lot of actually problems that hard to fix. Then definition of agents. So the term agents carries various interpretations, and while some view agents as fully autonomous systems, others see them as just simple workflows, kind of workflows using LLMs, not so deterministic that we used to use in programming. So these things we call agentic systems, and the agents are those which are making their own decisions. So in agentic systems, there are predefined workflows, which can be extremely powerful actually. And the agents is those which are planning and making their own decisions. So this differentiation helps in determining when a model can be kind of trusted autonomous tool and finding its own path. So when to consider agents, LLM features naturally tend towards complexity. And the key consideration lies in kind of whether the flexibility of an agent truly adds value to the specific use case, or actually adds more complexity. Because like agents typically involve higher computational costs, increased latency, much harder maintenance, higher risk of deviation. So, and in contrast, for instance, structured workflows, which we consider as a kind of contrary to the agents, can be much more suitable and much more predictable and cost efficiency for a bunch of tasks. Regarding the frameworks, so I guess many of us are familiar with ELIZA framework and others, which established the foundation for some kind of chatting agents in social context and introduced numerous useful tools. However, it doesn't fully address the fundamentals of building agents that aligns with their creators' intentions. So this leaves open questions about agent types, differences, and techniques, and how actually implement what you need. So, this is one type of agents which ELIZA-like frameworks that are, from my perspective, that are good to make an agent which does whatever it wants. If you want to make an agent which does what you actually want from it to do, you should probably start with something much simpler or even from scratch. So there is another type of ready-to-use solutions like LangGraph, Microsoft AutoGen, Crew AI, OpenAI Swarm. They provide high-level abstractions for multi-agent communications and also use of tools. So this is the example of frameworks which can accelerate development in the beginning. Then they might obscure important details, and debugging becomes much more challenging when like prompt and response visibility decreases. So starting with direct calls of LLM API often provides much better understanding and results. So on the example, on the screenshot is the worst method to use LLMs. This is just illustrates that sometimes we start using LLMs when we don't need to. And augmented LLM is the building block that that is kind of the most easiest to use, and which makes the main value which we couldn't get from without LLMs. So when LLM has appeared as a building block, first we started just kind of using it as a question answering system, and if we start doing that, we quickly realize that it doesn't work actually this way, because it generates hallucinations, right? And we actually should assume this as a processor for the data that we should put as an input. So in this case, if we control the data, so this augmentation process, then it becomes a tool that we can predictably use. This was actually the slide that I wanted to share for this part. So the first workflow pattern. So, and this presentation is built in a way of showing the pattern. So as we, in normal programming, when we start writing code without, let's say, functions, classes, object-oriented programming, paradigms, or like functional programming, we are getting some mess that is hard to control. And with LLMs, it's even worse, because LLMs are creating much more ways to go to the unpredictable results. That's why these patterns are actually needed. And and also probably for some patterns it's obvious that how to use them, and some patterns can be new to those who start building agentic systems. So the first example of the workflow is just a prompt chaining. So we break down the task into a few parts, and each result of one LLM call goes as an input to the next LLM call. So the use cases is kind of generating, for instance, of content, translating, copywriting, etc. And for each workflow, I show a simple example. And here we can see that that there is call the default block called GPT-4. In this case, it can be any other LLM. And example usage is marketing workflow for one input and one language, let's say, and we see that in the workflow, we actually call GPT-4 once with write the marketing copy, and then we call it once again with translate it to target language. So we have the simplest agentic system, which is not actually an agent, but already can do some powerful stuff. The second pattern is routing, and it focuses on classification to direct inputs to appropriate specialized processes. This might involve different LLM prompts for various query types, or allocating simpler tasks to more efficient models, while routing complex queries to more capable ones. This is a kind of straightforward approach. And this leads to significant can lead to significant efficiency boost. For instance, here is the example, and with routing, it's like we use if-else pattern, but on the level of LLMs. So in this example, for instance, these are two parts, right, of the code. And in this example, we have a function to route customer query. And let's look at how this looks when we call it. So for each query, we wrote customer query, put it as an input. And then as a result, let's get back to the function and see. So query goes in the classification prompt, and we ask LLM basically classify these as 1, 2, 3, 3 classes. Answer with one word only. So we expect that it will answer with one class. This is a kind of simplification. So actually you should use something like JSON formatting as an output, because it's much more reliable. But as just showing as a pattern, it will be all right. So as a result, we get the category. Here I would use JSON and some saved extraction of data from JSON. And then we have some handlers for each particular, basically it's a prompt for each particular class. And then we call GPT again with some category and with some prompt. And as a response, we have the response from LLM with some basically chosen prompt for generating this response. I guess it was pretty, it was clear. And the next one will be parallelization. It's we have much more. We will have some more complex approaches, but in the parallelization, I guess there is nothing nothing really sophisticated. What is important is that we can do some tasks in parallel if we assume that the result of these parallelized tasks can be also used as a separate step with LLMs, then we can call it in parallel. So let's check what this example shows. Parallel code review. And here we can use, this is in Python, right? But we can do it in any language. We run these calls to GPT in parallel, then we collecting the results in one array. And let's check what we have here. For instance, sample code to review. We run parallel code review. For each aspect feedback, we show the example, and so basically there is nothing else. So we can do the parallelization for the separate LLM calls, and it can actually make sense when we have some when we have, let's say, a lot of different, it can be batch processing or queries from different users, or just something that we have to parallelize for efficiency, at least because LLMs are actually creating a lot of latency, and you just can want to make your entire algorithm faster. Orchestration workers. This is the pattern where we have a manager or an orchestrator, which is delegating tasks to different parts of the system. And like, unlike fixed patterns like prompt caching or parallelization, this approach allows dynamic task allocation based on needs. So this flexibility particularly suits complex scenarios like code modifications where the scope isn't predetermined. Let's look at the code example. So take a while since I created these code examples. Let me check. We have the main function, and there is a task add input validation, and they're handling to all functions. So, and these functions, the input is actually list of files, text in the files, and this list can be actually an arbitrary length, and each file can actually require different types of processing. But here in this example, we just basically trying to parse it and process separately. So let's get first let's look at here. So updated files, we run orchestrator code update task and files. So task is this prompt, and files is the list of here is it is a dictionary with key as a name of file, and the value the text of file, text of function. And after we did this, we just printing that. So what we have in the orchestration code update, task and files as inputs. So step one, orchestrator creates a plan. So we create one separate prompt with a task as an input, with the list of names of files. So we don't even put the text here. And we write, create a plan for file changes, respond in JSON format. Here is the example that I mentioned before with how we should properly format the outputs from the LLM. So as a result here, and we actually run call GPT plan prompt. As a result, we will have the list of tasks to be executed. And then as we parse this JSON into the actual variable, and then we run on the step two, we actually execute for each file separate call to GPT-4, as we can see here. So the new prompt is update this file according to description, which is already in plan, which was generated actually, and the current content, we put here the text from the file. Provide only updated content. And as a result, we expect that LLM will actually follow our generated instruction to an arbitrary file, will return the result, and we will collect all the results into the list of results. And then we gather them, combine, and send as output. Next pattern is called evaluator-optimizer. And this pattern creates a feedback loop where one LLM generates content while another provides evaluation and critique. So the iterative process continues until quality criteria are met. This approach mirrors human editing processes and works especially well with clear evaluation parameters. So it's not it's not necessarily only when you have a clear evaluation. In some cases, you can use some tricks to still use this loop in various scenarios, but the main value of this is actually when you have some kind of testing function or environment where you can get some reasonable feedback on the results of what LLM has generated. And this is really powerful pattern. And let's look on the example which we have here. So here we have translation improvement workflow. And from what I remember, it is pretty interesting. So we have example usage. The early bird catches the worm, but the second mouse gets the cheese, and we want to translate it in this case to Spanish, and we set max iterations, which actually sets the restriction for this loop to not become an infinite loop. But the most interesting part is actually in this function, how it is constructed. So first of all, we run the simple GPT for prompt with translate to target language this text. And then we go to the list to the cycle to the loop of iterations, where we create the next prompt in the following way. Evaluate this translation, put here original test, put here translation, and ask if it's perfect, say perfect, otherwise explain what to improve. And then we, so basically we run this with GPT-4, and sometimes basically I made this example and tested how it looks like. So you can see something like, at first it says, well, the translation is not perfect. These are the particular problems in this translation. But after that, we take this evaluation, kind of what I just said, as their feedback, and putting this on the separate prompt and run it again with the prompt like improve this translation based on this feedback. And it tries to actually improve the translation according to the feedback, because we actually showed these focus points where it should look and what it should fix. And it can be actually not obvious, this idea that why, if LLM was not able to generate the good result, how should it be able to improve it if it hasn't been able to generate it? But it actually doesn't work this way. So when it generates something, it is just one data point in full subset of possible results that can be generated by LLM. And as we know that the relevant context is actually guiding it to better and better results. That's why when we run this separate evaluation step, we actually ask kind of the other instance of LLM evaluator to focus on the task of evaluation. It generates a reasonable context, and then we put this context again into the other LLM, into the other task of generating better or improving this quality of the translation. So, but it can be of course, used not only for translations. And as I said, if we have some environment which can give us a good evaluation of the results, it becomes really powerful thing. And one of the examples where it's useful when, for instance, you create a code generation system and you can put it into the results into some, let's say, static analyzer or a compiler. You can run the code and see the errors. And these errors are actually the most usable, the most valuable feedback that you can put into the feedback loop and actually improve the result. So, and here we approach the agents which are autonomous, which are not agentic systems. And autonomous systems represent kind of the evolution of agentic capabilities. And these agents begin with an objective or directive and autonomously determine their path to it through tool utilization, environmental data collection, and iterative progress that they work towards task completion. And while this autonomy proves powerful for open-ended challenges, production environments benefit from certain safeguards, like testing protocols, protective boundaries, iteration limits. All this stuff is actually needed because you kind of let LLM and the agent do whatever it wants, and it drastically increases the chance that it gets somewhere where you didn't expect it to be. So here is the example that I guess pretty useful for understanding all the aspects of this approach. So here we have a class of minimal agent, and we define the tools explicitly. So we say there are some tools that you can use, right? For instance, here we say search docs tool, calculate something, write file. The tools have the names. The names are important. So because the code, the LLM looks at them as a text. So it should decide whether tool to choose. That's why you should actually describe them properly. And also we put the tool description to actually, again, help it choose better. Search docs, available arguments are pricing. So I'm describing the arguments in the plain text here. Available arguments are pricing, features, returns, text. Calculate. The argument should be a numerical expression that will be executed as eval in Python interpreter, returns the output. So like LLMs can make mistakes in math in the calculation. So we define calculator as a separate tool. And the write file, the argument should be the text to be written in the file. GPT-4 function as usual. We implement these each tool separately. So search docs, there is a query is an input, simulate document search. And how it works, it returns is just basically key value storage. So it returns the text by the key. Calculate is just simple evaluation of expression. So if it asks for 2 plus 2, it will eval and we will get 4. Write file is just simulation of writing file, so we just return it and print that if LLM has called it, then it does it. And here is how the main cycle is arranged. Get next action function in this class, and it has tasks as an input and context as another input as dictionary. And what it does, it decides next action based on task and current context. So this is a separate function which is specifically made to ask LLM which action to take next. To make this decision, it should get all the relevant context. So that's why we create the prompt which contains the task, the available tools, the current context, which we are taking on each step. And here is the task, here is the prompt determine the next action to take based on the current context and available tools. Previous results can be referenced using result X, where X is step number. Respond in JSON format like this: tool name, arguments. If task is complete, respond with this. As you see, we also show the previous context, previous steps that it already executed, because this is how it should operate. It should know what it did before. It should know which task it is executing now. It should know which tools it has. So, and a separate function is actually execute this action that it just chosen. And in execute action, we have the particular action that has been chosen and the context, the same thing. So we keep this context between function calls. And if action is task complete, we just stop and exit. If not, then we actually get this tool from this dictionary, which we just chosen. If not tool, again, we say it's a mistake. We show tool not found. Arguments, we take args. And then, so basically in this cycle, we are basically executing the replace context reference scenarios if any. Here is it. So what I'm looking for, tools args. So this is the actual execution of this tool. So all this code was basically to get to these 1 points to actually call what we have chosen using the LLM. And solve task is just the aggregation of all this stuff. So this is main agent, kind of main agent loop, right? So we, on the next example, we'll see that we can create the task like create a pricing summary, search for pricing information, calculate the yearly cost for basic plan, write a summary to a file. So it's extremely arbitrary way of defining the task. So you could not do this via normal programming without LLMs and the agentic approach. And we call agent solve task. And what it does, let's see. We are just printing all this stuff. So here we see the outputs. So it prints what it's doing. And then it says planned action tool search docs. So it decided to choose this tool, which is called search docs. And it decided to put here pricing because it looked at how it is defined, that it knows that it has to put pricing or features as an input. So it actually decided to put pricing as an argument. This is what it get as a result. The result was basic plan is $10 per month. So it got the arbitrary output and also pro plan, but it knew that it should find basic plan. And it decided to take the number $10, which we see on the next line. So planned next action was to calculate 10, which it took from this part, basic plan cost 10, multiplied by 12. Obviously, it's 12 months because we asked calculate yearly costs. So LLM created this action, and then it get to the actual execution, and the result that we got after eval, we have 120. Then it decided to go to the next action, which is write file. So it chose write file, and what it put as the arguments was the text. The yearly cost for the basic plan is $120. The result successfully wrote, and then next action, it chose task complete without the arguments, and we have task complete. So this is how it handled this minimal agent handled the arbitrary set of instructions. Here I just wanted to show the example how the coding agent that we use, for instance, in Cursor. If you use Cursor, the composer, for instance, it can be arranged this way. So there is the interesting part that I mentioned. So there is environment. So when it can go to search files, return paths, write code, see the result, status, test, results, steps, etc., etc. So this is the full agentic way that coding agents have. So of course, to build effectively the agents, you can combine all these patterns, so you can decide which one is good for which goal, for which purpose. Start with small, right? Then expand to something that you need. Complexities, as I said, can lead to something that is hard to debug. Yeah, basically, I guess I shared all the information. I would probably say a few words about the project that I'm working on, and I would be happy to get any questions. So here you can see the projects that I personally somehow involved in. I'm happy to chat on any of them in Telegram chats. Yeah, let's switch to the questions, if any.
Okay, amazing. I think we have a few questions in chat that we can go over. First one is from Rashid. This is still workflow, right? It's not MAS question.
MAS, what is MAS? Sorry. Multi-agent systems, look, multi-agent system is a separate part, a separate thing. So it's kind of in different directions. So for instance, if you take one agent, it can be even in the very first example. When you have prompt chaining, you can say for the first part that you are a creative director. You have your task is to create top 5 ideas for this topic to be described, to be like written in content. Then you have a separate prompt which is described like you are let's say copywriter. This is the task for this is the topic for which you have to write some comprehensive I don't know, tutorial, and this is already a multi-agent system. But also you can make a multi-agent system easily via tools, frameworks like Crew AI, for instance. And there you do basically the same stuff, but there it has some particular spaces where you write you instead of you are the creative director, you write role creative director. You write the task, you write creating the tutorial, and there something else, and it is connected via this framework. But it is not actually giving a lot of value to the actual results that you are getting with your multi-agent system. In what is valuable in multi-agent systems is that you can effectively separate the parts into the agents, and this is much easier to control compared to the scenario, for instance, which I showed in the last part, when you have one agent which should do whatever you want. Like you expect that it will be able to, for instance, control 100 tools and do like 100 different tasks. In this case, it will like constantly failing. But if you will separate it to, let's say, 5 different agents, each one has, let's say, 10 tools, and you set clear workflow from taking taking on the task, then you make this system reliable. Yes, it's multi-agent and it is controllable, but there is nothing else between multi-agent and workflows. It's just the way of exchanging the data between the components of the system.